Hi, I'm Jeff Myers. I'm here to talk about classifying APIs for clear contracts. There will be more than just that to this talk, but I'm a sucker for alliteration. To introduce myself, I'm a software engineer at Rapid7, which is a security software company. For the past 8 years, I've been working on Insight IDR, a product that collects and processes 150 billion events a day to help customers detect and investigate hackers and other malicious activity occurring on their corporate systems. During this time, I've been involved in the design and implementation of many APIs for my product and for the Rapid7 cloud platform as a whole. Often this work requires collaboration across engineering teams spanning the globe. The purpose of this talk is to share a classification system we came up with at Rapid7 to describe the types of APIs we produce. I think the classification concept has been very useful for us and might be a helpful way for others to think about and discuss the types of APIs they create as well. I'll discuss the benefits both in terms of how they have helped us clarify our communication and specifying requirements, as well as how they've helped us standardize on technical solutions to common problems faced by our APIs. For a bit of context, let me describe some of the challenges we're facing at Rapid7 that led us to create our API classifications. We're a multi-product company dealing with different aspects of cybersecurity. Our products are built on a shared cloud platform where we've implemented common components to handle authentication and product access, data collection, audit logging, role-based access control, and a bunch of other features. For a company of our size, we have what seems like a ridiculous number of engineering offices spread across the US, Ireland, and Canada. We encourage team-oriented development with full engineering ownership end-to-end from the code, build, deployment, monitoring, and emergency response. Our teams generally get to pick the tools and technologies they'll use to solve their problems, but we encourage using some patterns and practices to avoid reinventing the wheel too much. Because we have so many distributed teams working on common and divergent projects, we found coming up with a common language as a significant benefit for mutual understanding. My personal goal is that every engineer and product manager at our company will immediately understand the meaning and implications of the differences between our API classes at Rapid7. All right, I'm going to start with some terminology I'll be using in this talk. I'm using API in a loose sense for a programmatic interface that two or more systems use to communicate with each other. There are many types of APIs, but most of this talk is focused on REST HTTP-based ones. The classification concepts apply to many other types of APIs as well, including messages or events, persistent data formats, code libraries, and schemas for shared data stores. Talking about APIs, I'll be using two terms for the roles involved. I'll use provider for both the systems and development teams responsible for implementing and maintaining an API that accepts requests, and consumers as a system and development team that will make requests to the provider's APIs. It's really useful to consider formal API design between development teams or between our company and our customers as a contract, an agreement between the two parties of how the API works. Our use of contracts is informed by the practices of consumer-driven contracts and contract-driven development, but is mostly a social standard rather than based on rigorous acceptance testing. We have experimented with using a project called Pact for doing code-based contract testing, and it's a very cool option. In a contract, the provider is responsible for implementing the agreed-upon contract and trying their best to provide the service to their consumers. Depending upon the type of API being developed, the contract can be more or less formally defined. The way I think about it, the more distinct consumers of the API you have, the more seriously you should take the API contract design. An API designed for use across two teams can be less formal than an API designed for use across all products or teams. We take the APIs produced for external customers extremely seriously because there are many customers using our APIs and they're paying us money. We strive to make our customer APIs as easy to understand and use as possible and prevent introducing breaking changes whenever we can. In these diagrams, by the way, I'm using that little 7 logo to represent an internal system or team. A few years ago, a bunch of Rapid7 engineers from across the company gathered together to nail down common guidelines for API design at Rapid7. One of the first things we agreed upon was a need to classify the different types of APIs our engineers create, based on the type of contract the API provides and the accessibility of the APIs. Accessibility refers to how the API is accessed, whether it's open to be called from the public internet, whether it's secured to be accessible only by other Rapid7 systems, or whether it's only accessible within a private VPC network in a single AWS account. From a contract perspective, we came up with the terms public, protected, and private to describe what consumers the API contract applies to. Public APIs are meant to be consumed by our customers. Protected APIs are meant to be consumed by other teams at Rapid7. And private APIs are intended to be used only by the same development team that produces them. Based on the combinations of visibility and contract type, we use these numeric classifications to describe our types of APIs. I'll go through each one of these in turn. Our Class 1 APIs are our most important, the ones we produce for use directly by our customers. Our customers use these APIs to programmatically interact with our products, to extract information to integrate with their own internal systems and other products, to automate responding to security issues, and to generate their own reports on the data we provide. Class 2 APIs are accessible to the public, but have a private contract, like the APIs used by our product's front-end JavaScript to talk to the back-end services. Sometimes customers develop their own integration with these APIs since they're publicly accessible, but we don't have a supported contract with them, and we can make changes to these APIs with less concern about breaking outside consumers. Class 3 APIs are for service-to-service calls between Rapid7 development teams across AWS accounts. This is the class where we work to integrate our products and to make sure that we can use shared components and features of the platform. Class 4 are APIs intended for use only by the team that produces them, usually within a single product or component. The purpose of this class is to ensure the team has as much flexibility to make changes to their APIs as needed. This allows the team to make improvements and to add new features without concerns of breaking outside consumers. Here's the full list of classes again. In the rest of the slides, I'll include references to the classes I'm talking about to help keep them straight. When creating any API, we found it very useful to have a firm understanding of what class it is, and using these terms when talking between teams and developing stories with product managers. Picking the class makes us more thoughtful and deliberate about the design of the API. In any case, the first point of API design is understanding your consumers, who they are and what they need from you. It's extremely difficult to design a good API when you're dealing with theoretical requirements rather than concrete problems that you're trying to solve with real people. For the Class 3 APIs, we work with the engineers across teams to negotiate a contract for the API. to collaborate on the design to ensure that the needs of both sides are met to achieve the goals of the project. Usually one side or the other makes and documents a proposal for the API with as much specificity and detail as possible. Then the proposal is reviewed and adjusted by everyone involved until we get to an agreement. The documented API contract becomes a spec that the teams can reference in the implementation, but can also be adjusted as needed when reality hits as coding and testing get going. API contracts don't often remain frozen. They are modified and enhanced as requirements change and additional consumers show up to use them. Here's a lazy graph I created showing roughly how much effort we put into contracts by API class. For Class 1 APIs, the public APIs made for customers, we take extra care to design them to make our customers' experience as positive as we can. We make use of more stringent standards for common API patterns like paging, versioning, response codes, and naming conventions. This makes our public APIs feel consistent to customers despite being implemented by many different engineering teams. We also make extra effort to fully and accurately document the APIs that we produce for our customers. Class 3 APIs involve cross-team negotiation that I mentioned previously. These aren't quite as serious as we can reach out to our coworkers to get changes made when needed. For the classes with private contracts, 2 and 4, our engineering teams are free to be as casual or as formal with their API design as needed, so long as the functional requirements are met. This has great benefits to being able to move fast, to do experiments, and to make improvements without needing to worry about breaking outside consumers. The only contract that we have support with is with ourselves. So long as the deployment works, we're good to go. Standardizing the support for our API classes has also been helpful. It helps emphasize the importance of being thoughtful and deliberate ahead of time, knowing how long you could be living with your mistakes. All of our API contracts are intended to be forwards compatible with changes. We're free to add more fields, optional parameters, and new APIs as needed. But any breaking API changes are taken seriously. For Class 1 APIs, when breaking API changes force us to release a new version, we will notify our customers that the old version will be removed 1 year after the announcement. During that time, we have to maintain both the new and old API until the time period passes or the last consumer is gone. Having a good monitoring strategy for keeping track of who's using what API versions is really helpful here. If after the year passes, we find customers are still using the old API version, we proactively notify them about the termination of the version and help them adopt the new version as needed. For Class 3 APIs, we have a better understanding of who at Rapid7 are using our APIs and how to pressure them when needed to update to the newer version. Our standard here is we notify the consuming engineering teams about the new API version and give them 3 months to adopt the new API version. Monitoring, again, helps here to cut things off after the last consumer is gone and to avoid production problems if there are laggards. Here's a quick overview of some of the types of breaking changes to an API contract, where we'd have to release a new version of the API. Sometimes we determine through monitoring that released APIs are not under active use, and we can sneak in changes without releasing a new version, but that's a pretty unusual situation. Even harder than the changes listed here are when there's a fundamental shift in how we model a domain or significant feature within our product. In that case, we're not just asking our customers to make minor changes to how they interact with our APIs. we're asking them to rework their whole integration to follow our direction. These situations are much more challenging, as we may need to give customers longer than a year to adapt, and the technical challenges of maintaining simultaneous support for both the old modeling and the new can require very substantial effort. On the technical side, there's also been great benefits from standardizing on API classifications. It has helped us a bunch to develop common solutions to many technical challenges. The first standard I'll talk about is the methods of authentication of APIs. For Class 1 APIs, we provide the customers the ability to create and manage API keys that they can use to access their products and data programmatically. This key management is a shared component that's common across all our products. When customers make requests to our APIs, they provide their key as a request header. For our Class 2 APIs, we make use of session cookies that are sent to the browser on login. These cookies are accepted by the backend services for all our products and components. There is a shared service that generates the session and provides validation and identity back to the backend services. This enables a single sign-on experience across our products. The session timeout and auto logout experience is also the same across our products and configurable by our customers. For our internal Class 3 and 4 APIs, we have a common approach of authentication of our APIs using consumer-specific API keys. We have a practice of implementing separate backends for each API class needed. This helps keep the authentication approach simple in each backend application. More importantly, it reduces the risk of an API being exposed to the wrong consumers. For example, exposing data across customers. We even include the API class within the name of the backend apps to help keep this clear. We've also standardized the use of particular request headers for our internal APIs. The consumer header is passed in requests to identify the caller of the API. This helps the provider identify the consumers that are causing load and errors to occur in their applications. The header is useful to identify usage of deprecated versions of the APIs. It's also used as part of the authentication of Class 3 and 4 APIs. The correlation ID header is an identifier used to trace individual requests across multiple systems spanning all API classes. A random UUID is generated at every entry point into our systems, then passed along through the entire data processing chain, being logged along the way. Passing and logging a correlation ID is very useful for investigating errors between systems. When a problem occurs, the engineers on the provider and consumer side can exchange correlation IDs to trace what API calls were made, investigate the data that was passed across the API, and which customers were involved. For the most part, we've standardized around the technical infrastructure we use to deploy, manage, and monitor our environments. Almost all of the Rapid7 platform runs on AWS. We use Kong as the API gateways for entry points into our environments from the public internet, particularly for our Class 1 and Class 3 APIs. Terraform is used to create and manage our infrastructure, following infrastructure as code. In addition to our AWS infrastructure, we use Terraform to configure our Kong instances as well as our Datadog monitors and some dashboards. Here's a diagram of the standard way we approach our Class 1 and Class 3 provider applications. We make use of elastic load balancers at the edge and in front of the backing applications. Kong is used to handle the authentication and routing of the API requests to the appropriate backend application. At each stage of this chain, metrics are sent to Datadog. This is an example of how we configure our class 3 Kong clusters with Terraform. It specifies the location of the target application and the routing rules used to direct the request. It grants access to the specific API paths and HTTP methods that are allowed on the target app. And finally, and most importantly, it lists which consumers are allowed to access the APIs. This is a key decision we've made with our approach to Class 3 APIs. The providers are in control of which consumers are allowed to access their APIs. Consumers must request access, and providers have the control to banhammer consumers if they're being extremely naughty. By standardizing on this approach using Kong, we've been able to leverage common solutions to provide a single API endpoint to our consumers that through configurable routing rules get served by multiple backing applications. Kong handles the authentication of our Class 1 and Class 3 APIs. For our Class 1 APIs, a Kong plugin will call out to another backend service to validate the API keys. That service will return a JWT containing the information about the customer and the individual user. The JWT is then passed with the request to the backing app. For Class 3 APIs, a Kong plugin validates the pair of the consumer header and the service API key, then forwards the request to the backing app. We've also implemented a common mechanism for rate limiting our Class 1 API calls in Kong. This gives us the ability to tune the limits per customer and API endpoint. Our Kong cluster also collects and sends metrics about API usage to Datadog. For the Class 3 APIs, the metrics include the consumer header in the tags of the metrics, allowing for easy analysis. Here's an example of a dashboard for a specific Class 3 backend application, which shows a metric of requests broken down by the consumers making the requests. This is shown in the graph in the bottom center there. The standardized metrics reported by Kong also allows us to automate the creation of Datadog dashboards using Terraform. Anytime a new application is added to our Class 1 API, it's a quick Terraform operation to generate a new Datadog dashboard for the app. Here's the resulting dashboard generated by the Terraform code. The same approach is used to automate the creation of monitors for our applications using Terraform. Here's the resulting monitors generated by the Terraform code. We also make use of the consumer and correlation ID request headers in our application logging. By tagging logs with these properties, we can easily identify what consumers are causing errors and warnings, observe the pattern of usage by different consumers, and chase down logs associated with specific requests based on the correlation ID. We also put into our Terraform code information about the engineering teams that are responsible for each of the consumer applications. We record an email distribution list for the team, their Slack channel, and what office they're located in. You know, back when people used to work in offices. This may seem simple or an overkill, but it's really handy to quickly know how to get in touch with who's consuming your APIs when things go wrong or when you want to discuss API changes. Like, I see you're using this one API. Are you actually using this field in the response, or would you care if I remove it? Knowing who to reach out to is especially useful for engineers who didn't work on negotiating or implementing the API in the first place. I'd really like to add the consumer's PagerDuty service to this metadata so that we can page the appropriate on-call engineer in case of an emergency. Looking forward, we're actively working on exposing some portions of our product and platform features to our customers using a GraphQL interface. We're working through some challenges of providing a good and consistent GraphQL experience, following the patterns we've established with our Class 1 REST APIs. We're looking into using GraphQL federation to combine the graphs from multiple backend services together to be exposed from a single endpoint, like our existing REST APIs. This is challenging because we'll need to mix different and sometimes conflicting domain representations of resources without confusing or frustrating customers. As an example, we're trying to work out how to present an asset looking one way in one portion of the graph and a different way in another area of the graph. We're also working on how we'll consistently present the API documentation from a consolidated federated graph. Wrapping up, here's the API classifications we're using at Rapid7. By setting up these names and consistently using them across teams and products, we fostered a common understanding of requirements and responsibilities across teams. It has made discussing and negotiating API contracts clearer. Standardizing on these classifications has also helped us create common solutions to routine problems like authentication, monitoring, and the diagnostics of APIs. I hope this approach to classifying APIs may prove useful to you and encourage you to come up with your own classification schemes for the APIs you create in your own work. Thanks for your time and attention.